Welcome you all in the lecture number 12 of Abstract Algebra MTL 6051. In this lecture, we will going to discuss Sylow first theorem, Sylow second theorem, Sylow third theorem and some examples related to these theorems and Cauchy theorem for finite abelian group. Let us see Sylow first theorem. If G be a finite group and p to the power n, where p is prime number, what is p? P is prime number. G be a finite group, remember that G is finite, and p to the power n divides order of G, then G has a subgroup of order p to the power n. Okay. For example, if order of G is 100, then 2 to the power 1 divides 100. Then the theorem says that if 2 to the power 1 divides 100, what is 2? 2 is prime, right? Then this G has a subgroup of order p to the power n. Then G has a subgroup of order 2. Okay, and G has a subgroup of order 2. Similarly, 2 to the power 2 divides 100. Then G has subgroup of order 2 to the power 2. 5 to the power 2 divides 100. Then G has a subgroup of 5 to the power 2. Right? This is Sylow first theorem. If p to the power n divides order of G, then G has a subgroup of order p to the power n. Okay. Sylow p subgroup. Now next definition is Sylow p subgroup. What is Sylow p subgroup? Sylow p subgroup, in short we can call it PSSG. PSSG. P Sylow subgroup. Okay. Then if G be a finite group and p to the power n divides order of G, remember that p to the power n divides order of G and p to the power n plus 1 does not divides order of G. Okay. If p to the power n divides order of G and p to the power n plus 1 does not divide order of G, then subgroup of order p to the power n is called p Sylow subgroup or PSSG, right? Then if order of H is p to the power n, then this H is known as PSSG, p Sylow subgroup. Okay. Again, let us see, if G be a finite group and p to the power n divides order of G, but p to the power n plus 1 does not divide order of G, then the subgroup of order p to the power n is called Sylow p subgroup or PSSG. Okay. See the example. If order of G is 24, what is 24? 24 can be written as 2 to the power 3 into 3. Okay. 2 to the power 3 divides order of G, but 2 to the power 3 plus 1. Right? See the statement, p to the power n divides order of G, but p to the power n plus 1 does not divide order of G. Okay. Then what is order of G? Order of G is 24. This is 2 to the power 3 into 3. 2 to the power 3 divides order of G, but 2 to the power 3 plus 1 does not divide order of G. Okay. 2 to the power 3 plus 1 means 2 to the power 4, that is 16. 16 does not divide 24. Okay. Then definition of PSSG says that 2 to the power 3, then the subgroup of order 2 to the power 3 is called 2SSG. Subgroup of this order is called 2SSG. Similarly, 3 divides 24. Okay, 3 divides order of G, but 3 to the power 1 plus 1 does not divide order of G. 3 to the power 1 plus 1, that is 9. 9 does not divide 24. right? 3 to the power 1 divide order of G, that is 24, but 9 does not divide to 24. Then the subgroup of order 3 is called 3SSG. Okay. If order of G is 100, then what is 100? 100 can be written as in this way: 2 to the power 2 to 5 to the 2 to the power 2 divides 100, but 2 to the power 2 plus 1 does not divide 100. Then what the definition says that? Then the subgroup of order 2 to the power 2 is called 2SSG. Similarly, 5 to the power 2 divides 100, but 5 की power 2 plus 1 does not divide order of G, that is 100. Then the subgroup of order 5 to the power 2, the subgroup of order 5 की power 2, 5 to the power 2 is called 5SSG. Okay. Now let us see one theorem. Whether 2p-SSG is conjugate if H is subgroup of G and X is any element of G, then X inverse is also subgroup of G. Okay. Let us see whether this is true or not. What is H? H is subgroup of G, right? These we are talking about in terms of p-Sylow subgroup, p-SSG. Okay. If H is p-Sylow subgroup of G, H is p-SSG of group G, and X belong to G, X is any element of G, then X inverse is also subgroup of G, is also subgroup of G, right? And this is also p-SSG. Okay, let us see the definition. Whether this thing happen or not. H is subgroup of G. Let H is subgroup of G. Let us assume this. And X is any element of G. Then what is X inverse? It means X and one element from capital H, say small h, and from right side X inverse. What is H? H belong to capital H. And what is X? It is already given. It is from G. Okay, X belong to G and H belong to capital H. Whether this X inverse is empty? This is empty? No, it cannot be empty. Why? Since E belongs to X inverse, right? Why? This E is equal to X inverse. Since H is subgroup, therefore E belongs to H, and this is E. Okay. This X inverse does not empty. Then we have to show that X inverse is subgroup of G. And for subgroup we know that if AB belongs to H, this implies that AB inverse belong to H for all AB, then H is subgroup of G, right? Let us assume that A and B belong to X inverse. A and B belong to X inverse. Okay. Then there exist H1 and H2. See, A is element from X inverse, and every element of X inverse is of the type this X inverse, such that small h belong to capital H. Since A belongs to X inverse, then there exists, say, H1 such that A is equal to X inverse, and similarly B is equal to X inverse, right? This is written here. A is equal to this and B equal to X inverse. Okay. Then what is AB inverse? See, AB inverse is X inverse, that is A, and B is X inverse whole inverse. Okay. And this X inverse, and apply reversal rule here. Then X inverse whole inverse, H2 inverse, and X inverse. What is this? This is identity, right? Then this is X, H1, H2, X inverse. Okay, H2 inverse, sorry. What is H1, H2 inverse? Say H1, H2 inverse is H3. X of H3, X inverse. This belong to X, H, X inverse. It means AB inverse belong to X, H, X inverse. Okay, AB inverse belong to X, H, X inverse. Hence, X, H, X inverse is subgroup of G. Okay. Now see the example. If G is equal to D4, right, dihedral group 4, then consider H. What is H? H is generated by R180, right? What is this? R0, R180. Okay. If we operate R180 one time, this is R180, but R180 with R180, we operate this, then this gives us R0. Okay. Then there are two elements in R180, that is R0 and R1. What is this? This is subgroup. Say this subgroup is H. Okay. Say this is R0, R180. Okay. Now let X belong to G. What is G? G is D4. Then consider any element of X belong to D4. Consider any element of D4. Let us assume that X is R90. Then X, H, X inverse. What is X? R90. What is H? R0, R180. What is X inverse? R90 inverse. Right? And what is this? R90, R0, R90 inverse. And R90, R180, R90 inverse. Okay. After solving this, we got this is what? R0. This is R0. And what is this? This is R180. Okay. It means this is subgroup of D4. Let us see another example. Let K be a subgroup of D4 generated by H, that is R0 and H. Right? Again, let X is equal to R90. Let us assume that K is generated by H, then K is R0 H. Let X is equal to R90. Then what is X? K X inverse. This is equal to R90 K R90 inverse. Okay, and this implies that R90, what is K? K is R0 and H. Then right here, first R0, then H. R90, R0 and R90 inverse. Second, R90 H, R90 inverse. What is this? This is R0. And what is this? This is capital V. Okay. This gives R0 and capital V. This does not equal to K. What is K? K is R0 and H. What is K? K is R0 and H. Then this R0 H does not equal to R0 B. Okay. Say this is K and let us call it K dash. Then K and K dash are conjugate of each other. Right? The conjugate of each other. Then it is one of the natural question arises here that whether two p-Sylow subgroup are conjugate each other. Yes, answer is yes. That is Sylow's second theorem. What Sylow's second theorem says that any two p-SSG, any two p-Sylow subgroup of group G are conjugate. Right? If there are two p-Sylow subgroup, then they are conjugate to each other. Okay, let us see. If H and K are two PSSG, what is H? H is PSSG, and what is K? K is PSSG. H and K, let us call H and K are two PSSG. Okay, two PSSG. Then if they are conjugate, then there exists X belong to G such that K is equal to X H X inverse. Okay, see the previous example. In previous example, R naught and H, this is K. Okay, but there exists X, say R90 belongs to D4 such that R90 H R90K R90 inverse is equal to R naught V, which we call K dash. Then this K is isomorphic to is conjugate to K dash, not isomorphic, sorry. This K is conjugate to K dash. Okay, then these two, since they are PSSG, therefore we call it conjugate each other. These two PSSG are conjugate to each other. Okay. See the example. What is G? G is S3. Then we have to show that 2 SSG and 3 SSG are conjugate. Let us see by the example. S3 is identity 1 2 1 3 2 3 1 2 3 1 3 2. Okay. What is order of S3? This total 6 element factorial 3. What is 6? 6 is 2 to the power 1, 3 to the power 1. First you have to verify that whether it contains PSSG or not. Then what is the criteria for PSSG? P to the power n divides order of G, but P to the power n plus 1 does not divide order of G. Okay. And what is order of S3? This is 2 into 3. 2 to the power 1 divides order of S3. Okay. But 2 to the power 1 plus 1 does not divide order of S3. Okay. It means G has 2 SSG. Right? G has 2 SSG. Similarly, 3 to the power 1 divides order of S3. But 3 to the power 1 plus 1 does not divide order of S3. It means G has 3 SSG also. G has 2 SSG of order 2 and 3 SSG of order 3. Okay. G has 2 SSG and G has 3 SSG. Condition is only this. P to the power n divides order of G and P to the power n plus 1 does not divide order of G. Right? Then G has PSSG of order P to the power n. Then this G has 2 SSG of order 2 to the power 1 and 3 to the power 1 divides this. 3 to the power n plus 1 does not divide order of S3. Then G has 3 SSG of order 3 to the power 1. Okay. What is our problem? We have to show that 2 SSG or 3 SSG and 3 SSG are conjugate. Okay. See. 2 SSG in S3. What is 2 SSG in S3? 2 SSG in S3 is identity and 1 2. This is one subgroup. Say H1. Now say H2. Identity and 1 3. What is S3? I and 2 3. Right? These are the 3 2 SSG. Right? How many 2 SSG? How many 2 SSG? 3. Okay. And say H4 is equal to I 1 2 3 1 3 2. Okay. This is 3 SSG. How many 3 SSG? 1. Okay. Then we have to show that two SSG means H1, H2, H3 are conjugate to each other. Then what is the meaning of conjugate? If H1 is conjugate to H3, then it means that there exists X belong to S3 such that X H1 X inverse is equal to H3. What is this X? Say this is 1 3 H1. What is H1? Identity and 1 2 and X inverse 1 3 inverse. Okay, 1 3 H1 1 3 inverse. This is H3, right? You have to verify it. Okay, already this type of problem we discussed so many times, right? Then this H1 and H3 is conjugate. Similarly, 3 SSG, this is 3 SSG. Then this H can be written as identity H, identity inverse. So they are conjugate to each other. But one more question arises here. How many p-SSG exist? Right? For any in any group, any finite group, if p-SSG exists, then how many p-SSG? Right? How many p-Sylow subgroup exist? See the third theorem. Third theorem says that how many p-Sylow subgroup exist. The number of p-SSG is equal to 1 plus kp. Right? Number of p-SSG is 1 plus kp. Okay, but what is 1 plus kp? 1 plus kp must divide order of G. This number must divide order of G. Right? The number of p-SSG is 1 plus kp, first thing, and this 1 plus kp divides order of G. And what is k? K is 0 1 2 3 up to so and so on. Then this 1 plus kp we denote it in short form NP. Suppose 2 SSG, then 1 plus 2k, we can denote it 1 2. For 3 SSG, 1 plus 3p, we denoted N3. For 11 SSG, 1 plus 11p. Okay, and 1 plus 2k, 3k and 11k. We denoted N11. Okay. Now see the example. If order of G is 10, okay, then how many 2 SSG and 5 SSG? See how you solve it. What is order of G? This is equal to 10. What is this? This is 2 into 5. Okay. Then 2 to the power 1 divides order of G, but 2 to the power 1 plus 1 does not divide order of G. Then this thing, it is confirmed that 2 SSG exist. Okay, 2 SSG exist. Then how many 2 SSG? Say N2 is equal to 1 plus 2k. What is k? K is equal to 0, 1, 2, 3. That's 1. Say if k is equal to 0, then what is N2? N2 is 1. Then 1 plus kp means 1 plus k0. What is p2? Divides this number, divides order of G. Yes, true. Right? This divides order of G. Because theorem says that 1 plus kp must divide this. Then for k is equal to 0, 1 plus k into 2 is 1. 1 divides 10. It's true. But for k is equal to 1, see 1 plus 1 into what is p? 2. That is, this is 3. 3 divides order of G? No. 3 does not divide order of G. Again, for k is equal to 2, 1 plus 2 into p. What is p? 2. This is 5. And 5 divides order of G? Yes, true. Right? Then What is n2? n2 is equal to 1 plus 2k. This 1 plus 2k divides order of G only when k is equal to 0 or k is equal to 2. Okay. For k is equal to 0, n2 is 1. For k is equal to 2, n2 is 5. It means number of two Sylow subgroup is either 1 or 5. Okay. The number of two Sylow subgroup is n2 is 1 possible. n2 equal to 3 is not possible. Why? Since 1 plus 1 into 2, that is for k is equal to 1, this is 3. This does not divide order of G. So n2 is equal to 3 is not possible. What is this? This is not possible. Okay. Next. For n2 is equal to 5. How? 1 plus 2k. Right? 1 plus 2, k is equal to 2. This is 5. Divides order of G. It means n2 is equal to 5. This is possible. Means n2 is 1. Number of two Sylow subgroup is 1. And number of two Sylow subgroup is 5. Whether the number of two Sylow subgroup is 7? No. 1 plus 2 into 3, that is 7. 7 does not divide order of G, that is 10. Okay. So the number of Sylow subgroup 7 is not possible. Number of Sylow subgroup is 9. 2 into 4, this is 9 divides order of G, that is 10. It is not possible. Okay. The number of two Sylow subgroup is either 1 or 5. Similarly, 5 to the power 1 divides order of G. Yes. Order of G is 10. Okay. 5 to the power 2 does not divide 10, means 25 does not divide 10. Yes. Then G has 5 Sylow subgroup of order 5. Okay. Then how many 5 Sylow subgroup exist in this group of order 10? n5 is equal to 1 plus 5k. Put k is equal to 1. Sorry, k is equal to 0. If k is equal to 0, then this is 1. 1 divides order of G. Okay, true. Then n5 is equal to 1. This is true, possible. For k is equal to 1, this is equal to 6. This thing equal to 6. 6 divide order of G. What is order of G? 10. It is not possible. It means n5 is equal to 6. This is not possible. Then for k is equal to 2, this is 5 into 2, 10, 11. 11 not possible. Group of order is 10, then how 11 subgroup is possible? No? It is not possible. The number of 5 Sylow subgroup is only 1. This condition for k is equal to 0, only this number divides order of G. Okay. The number of 5 Sylow subgroup in a group of order 10 is 1. Okay. Now let us see one more important result. See, in above example, if order of G is 10, right, that is 2 into 5, then number of 2 SSG is either 1 or 5, and number of 5 SSG is only 1. Okay, see here 2 SSG, right? 2 SSG is either 1 or 5, but 5 SSG, this is 1, means this 5 SSG is unique. 5 SSG is only 1. Then the theorem says that, next result is that, theorem says that if p-SSG is unique, p-SSG, what is p? P is 5. 5 SSG is unique in a group of order 10, then this 5 SSG is normal. See, this is one of the important result. Okay. Theorem says that if p-SSG in a group G is unique, then this p-SSG is normal. Okay, and conversely, if the p-SSG is normal, then this is unique. Okay, let us see the proof. First part, let us see G be a finite group and has p-SSG of order p to the power n. G has unique p-SSG of order p to the power n, right? We call this p-SSG as h. Okay, then order of h is p to the power n. Since it is p-SSG, for p-SSG we know that p-SSG exists in a group G if p to the power n divides order of G, but p to the power n plus 1 does not divide order of G. Okay. Then order of h is p to the power n, and p to the power n does not divide order of G since it is p-SSG. That's why this condition holds. Okay. Let x belong to G. Then what is x h x inverse? This is also subgroup of G. Okay. This is subgroup of G. Then what is order of x h x inverse? We know that order of this is also p to the power n, that is order of h. It means x h x inverse is also p-SSG. Is also p-SSG. But we know, our statement is that G has unique p-SSG. G has unique p-SSG. It means h and x h x inverse both are same. This says that hx is equal to xh, right? It says that xh is equal to hx. This thing happened for all x belong to G. Then what is this? This is not definition of normal subgroup. It means H is normal subgroup of G. Okay. If p-SSG is unique, then this is normal. Okay. H is p-SSG, then H is normal. Conversely, if p-SSG is normal, suppose K is p-SSG and this is normal, then this is unique. Okay, then we will prove it. Let us assume there are two p-SSG. Okay, here conversely, let us assume that p-SSG of G is normal and there are two p-SSG H and K of G. Later on we will show that these two are equal. Then the Sylow second theorem says that H and K are 2 p-SSG. 2 p-SSG, then they are conjugate. Then they are conjugate. That is, there exists x belong to G such that x h x inverse is equal to K. Okay, x h x inverse is equal to K. Since p-SSG is normal, it is given. Na? Since p-SSG is normal, okay, then x h x inverse is equal to h. What is h? H is p-SSG. This is normal, and this condition hold by the definition of normal subgroup. Then this thing says that what is x h x inverse? This is K also. It means K is equal to h. What is K and h? K and h are p-SSG. Both are same. It means p-SSG is unique. Next, let us see the example. If order of G is 39, then subgroup of our order 13 is normal. Apply above theorem. Okay. What is order of G? Order of G is 3 into 13. That is 39. Okay. 13 to the power 1 divides order of G. This order of G is 39, remember that. But 13 to the power 1 plus 1 does not divide order of G. Then G has 13 SSG, 13 Sylow subgroup. Okay. Then how many number of 13 Sylow subgroup? N13. That is 1 plus pk, 13 into k. And what is k? K is equal to 0, 1, 2, 3, data, so on. Then theorem says that 1 plus kp means 13 into k divides order of G. This divides order of G only when k is equal to 0. And if k is equal to 0, then what is n13? 1 plus 0, that is 1. Means n30 is 1. n13 is 1. n13 is 1 means number n13 is 1 implies that number of 13 SSG, 13 Sylow subgroup is 1, is unique. That is 13 Sylow subgroup is normal. Okay, and this is normal. Okay, n13 equal to 1, this is possible. Then this is unique. Then above theorem says that if p-SSG is unique, this implies if and only if 13 SSG is normal. Okay. Next, if order of G is 21, then G is and G is non-abelian. Two condition is given. Order of group is 21 and G is non-abelian. Then how many normal subgroup of G? Right? See, order of G is 21. That is order of G is equal to 21. That is 3 into 7. See here, 3 into 7. Then 3 to the power 1 divides order of G. Okay. But 3 to the power 1 plus 1 does not divide order of G. Yes. The number of 3 SSG is 1 plus pk, that is 3k. What is k? K is equal to 0, 1, 2, data. Then this 1 plus 3k, theorem says that this 1 plus 3k divides order of G, which is 21. Right? This divides order of G when k is equal to 0, k is equal to 2. Okay. For k is equal to 0, n3 is 1. For k is equal to 2, n3 is 7. It means number of Sylow subgroup, number of 3 Sylow subgroup is 7. Number of 3 SSG is 7. Then this 3 SSG is 7. There are 7 3 SSG exist. It means 3 SSG is not normal. Okay. Okay. Then come to the 7 SSG. Okay. Come to the 7 SSG. 7 to the power 1 divides order of G, but 7 to the power 1 plus 1 does not divide order of G. Right? The number of 7 SSG is 1 plus 7 into k, and 1 plus 7k divides order of G, which is 21. This divides order of G only when k is equal to 0. Right? K is equal to 0, then n7 is 1. What is n7? n7 is 1. This implies that number of 7 SSG is unique. And above theorem says that if this 7 SSG is unique, then this 7 SSG is normal. Right? But we know that there are two other normal subgroup. There are two other normal subgroup. One is E and one is G, and other one is 7 SSG. So if order of G is 21, then there are three normal subgroup E, 7SSG and G, that is 1 plus 1 plus 1. Three normal subgroup of order of group of order 21. Okay, this is the answer. Number of normal subgroup of group order 21 is 3. Next is Cauchy theorem. See the statement and proof we will see in next class. If G is finite abelian group and P divides order of G, then there exists an element which is not identity and a to the power P is E, right? For example, if order of G is 30 and 5 divides 30, then there exists A such that order of A is 5, right? If and same statement is this, if G is finite abelian group and P divides order of G, then G has an element of order P. These two statements are same. Okay. Proof of this theorem we will discuss in next class. Okay.